Hello, I'm Mr. McBrien. This is SCH4U, Trends in the Periodic Table Revisited. So, we've been discussing for 2 years now chemical and physical properties of various compounds and elements. And more we've been starting to explain these in terms of the outer shell electrons. Things like ionization, reactivity, bond types, all of these are associated with the orbitals in which electrons are located and with the electrons that are around these, the proximal electrons. We have a key tool, which we've been using since grade 9 now. The periodic table sorts elements based on the configuration of outer shell electrons. So it'll always be a tool we can use to investigate phenomena to do with reactivity and these kinds of things. But now we can begin to examine the properties of an element in terms of fundamental forces within the universe. So many of the properties of these elements are related to the force of attraction between the nucleus and the electrons. And it's a good idea for us to go back to physics class and talk about the force of attraction and how it is defined or how it is decided. We get to Coulomb's law, which talks about the electrostatic attraction between charged particles. When you think about it, an electron is a charged particle, and the nucleus is a charged particle. So if we want to look at the force between these two things, we can go right back to Coulomb's law and talk about the force in terms of the charge of the nucleus, which is the number of protons, the charge on the electron, and the distance between the electron and the nucleus. So if we take the Bohr model, we have carbon here with 6 protons and 6 neutrons in the nucleus, and 6 electrons on the outside in order to balance the charge. If we want to look at then the force between these things, which is going to decide many aspects of this element, the distance between the nucleus and the valence electrons increase. Well, this is going to decrease the attraction. Electrons in the higher energy levels, which have an average distance which is greater, the average distance to the nucleus is greater, while these are going to have less force attracting them. Now, the other factor which we can consider is the number of protons in the nucleus, or the nuclear charge. Again, Coulomb's law suggests that that will be proportional. So as the nuclear charge increases, the force of attraction for the nucleus, or between the nucleus and the electron, increases. Now, so what we're going to see then is that force is going to pull electrons closer if that force is higher. And we can measure this in terms of the atomic radius, the radius of the atom itself. So we'll see trends in 2 directions. As we go down a given group, the electrons in the higher energy orbitals are going to be further from the nucleus. And this means that the radius is going to increase as we go down a group. And we can see a pretty clear trend in this direction as we go down. Now, in contrast, if we go across a period, so choose any one of these rows, we can see that the nuclear charge is increasing while the distance for the electrons, because they're in the same energy level, isn't increasing. So greater nuclear charge implies Coulomb's law will say that the force is greater. It means the radius decreases as we move to the right. In other words, they're holding on to the electrons more tightly as we move to the right-hand side. Now, there's a difference between the atomic radii of an uncharged atom versus a charged atom. So we can look at some metals here, and as soon as we pull off a single electron, for example, taking lithium from the neutral atom to its ion, we can see that its radius drops immensely. And this is a pretty clear trend across all of the metals. But our overall concept remains the same. So as we go down a group, the radius gets larger. And in fact, this incredibly busy slide, which I'd encourage you to pause it and think about it for a little while, this amazingly busy slide describes just this. The ions are shown in gray, whereas the uncharged metals are in this bluish gray, and so on. Well, you can still see that these trends follow. The radius goes up as you go down through the groups. So that radius will impact various things, including crystal sizes and things like this, crystal forms, and various aspects of compounds that are associated with those elements. Now, there's another interesting trend to do with those electrons. And first off, it's good for us to review the photoelectric effect. In the photoelectric effect, electrons are ejected from a metal surface if they're hit by EM waves that have the appropriate energy. If they have enough energy to exceed a certain threshold, the ionization energy for that metal, they'll eject an electron when they hit it. And this is called the photoelectric effect. And of course, it was a key tool in understanding quantum mechanics. Now, the photoelectric effect allows us to measure the ionization energy for these metals. That ionization energy itself is an insight into how well those metals are, or how tightly they're holding electrons. So the ionization energy is defined as the energy required to remove one electron from an atom in the gaseous form. The first ionization energy is the energy that's needed to remove the electron furthest from the nucleus, causing, of course, a single unit charge on a cation. And there's a formula for this first ionization. The atom plus energy goes to the cation plus an electron. But we can continue ionizing these further. So there's a second ionization energy in which the cation is hit with more energy and kicks off another electron. Third ionization energy, etc. Now we can get some insights into the way that electrons are held by an element by measuring these first, second, etc. ionization energies. So let's try that with beryllium. Beryllium has 4 ionization energies because it has 4 electrons that can be kicked off. So we can go from its ground state uncharged electron configuration through to a singly charged cation, doubly charged cation, 3 and 4, once we've kicked off enough electrons. And as we do so, of course, the electron configuration, as we've learned, moves to through the other elements, the same electron configuration as the other elements. Now, if we take and we measure these ionization energies, we see something interesting. We can measure them, and then we can relate this back to the properties of the element itself. So when we measure the ionization energies for beryllium, kicking the first electron out to distance, infinite distance, the ionization energy is about 900 kilojoules per mole. To kick off a second one is about double that. So the second electron that we want to kick off is held tighter than the first. And that's not altogether shocking for reasons we may get into at some point. But something interesting happens when we move to the third ionization energy. When we do this, the increase is approximately 10 times. So this third electron is held much more tightly than the others. And then the next electron, to kick it off, is a small increase percentage-wise from the third electron. So what we have is we're not altogether surprised to see that the ionization energy increases as we keep going, because with each electron that's gone, the net positive charge increases and it becomes more difficult to remove those electrons. Not a great shock. But when it comes to beryllium, there's a tenfold increase when we go from the second to the third electron. So that's a pretty interesting result. What we can infer from this pretty simply is that two of the electrons in beryllium can be easily removed, and the other two, it's extremely difficult to get them to remove them. Well, we can relate this right back to valence electrons and beryllium winding up in the same electron configuration as neon when we remove two electrons. Now, if we, so this is interesting, we can certainly talk about the energies of those electrons and things like this, but we can also start to look at the first ionization and look at the trends in this across a row and through a group and things like this. Again, we can get insights into which electrons are held more tightly by how much energy is required to remove them. And so this is a graph of the first ionization energy in kilojoules per mole as a function of atomic number. And at first it may look sort of random, but in fact it really isn't. So we see a trend upward across, going from hydrogen to neon, a dramatic drop in ionization energy, and then another trend across the periodic table, across the periodic table as we move through, going back to our noble gas, which is hard to ionize. And once again, we see this trend again going from the alkali metal through to the noble gas. So we see this increase in ionization energy associated with that, associated with movement across the periodic table. If we move down a group, the ionization energy actually decreases because the highest occupied orbital is further from the nucleus. So our trend, if we want to just choose the noble gases as a group to study, the trend is down. But if we were to choose any of the items in a group, the trend is again down for each one of those. If we take our alkali metals, for example, again the trend is downward. So then we can go ahead and look at something slightly different, electron affinity. So electron affinity is like the mirror image of the ionization energy. It's the amount of energy that gets released when an electron is added to a neutral atom. So the neutral atom receives an electron and moves to the anion form and gives up some energy in so doing. So this trend will look very similar. The only difference is that it's shifted by 1. So the noble gases have the lowest electron affinity. They have no interest in that. In contrast, well, so you can see the general trend here. This is an overlay of the ionization energy, the first ionization energy, versus the electron affinity, and you can see it's actually shifted by one mass number. Now there's some interesting exceptions to the trends in the ionization energy which merit some discussion. These might seem like some random error and we don't need to worry about it. And you might suspect that were the case, except that you can see that these are in exactly the same place. And if you notice, they're 3 units apart. So they're 3 electrons apart. So what I'd encourage you to do is have a look at the electron configuration and see if you can attribute something to these deviations from the trend. So beryllium's more than boron, nitrogen's more than oxygen, magnesium's more than aluminum, and phosphorus is more than sulfur. Have a look at a couple of those. And so draw the energy level diagrams of 4 of those exceptions and see if you can come up with an explanation for that. Go ahead and pause the movie, please, and see if you can come up with that yourself. And if you want a little help, you can look at Chem Guide for some additional hints for that. Okay, welcome back. So hopefully you've drawn up your electron configurations and you've drawn your own conclusion about where this deviation from the trend comes from. I'll give you my take on that now. So if we look at the electron configurations for beryllium and for boron, we can see them here. And as a reminder, we've got beryllium. It's harder to pull an electron off of beryllium than it is to pull one off of boron. Well, it's worth noting that boron's outer electron in that 2p orbital is in a higher energy orbital. It's slightly further from the nucleus. And so a little less energy to ionize, even though it's got a higher nuclear charge. By the way, if you looked at magnesium and aluminum, it should have a similar explanation since they're, of course, below each other. Now, if we want to take the nitrogen and oxygen case, it's a slightly different situation. Here's nitrogen and here's oxygen. Okay, and the difference is between this electron here and this one here. And so it takes more energy to remove this electron than it does to take this one. Well, these are in the same energy levels, so they shouldn't. That explanation that we had for beryllium and boron shouldn't apply, of course. Well, what we have in this case, there's actually repulsion between the 2 negative charges. Remember, the like charges repel each other. So because those are occupying the same space in the 2p orbital, it takes a little less energy to pull that electron out of that orbital because the other one's kicking it out. And phosphorus and sulfur have a similar explanation if you have a look at their electron configurations. Okay, so in summary then, many of the properties of compounds and elements, including their reactivities, are related to outer shell electrons of the atoms and of the ions. The behavior of these outer shell electrons is related to their attraction to the nucleus and also, in some cases, to the proximal electrons around them. and the influence of the electrons around them. We can see some clear trends associated with things like the atomic radius and to the change in the overall charge in the nucleus. So these are some interesting aspects that we can get out of our newfound knowledge to do with outer electron configurations. So please go ahead and read over the note for today and go ahead and work your way through the worksheet. Don't forget that the answers are also available in the answer key for the worksheet. Thank you very much and have a great night.